Good morning, everyone. I'm Johannes Wegmeier, Assistant Professor at Stevens Institute of Technology, and I welcome you to this week's episode of our A Closer Look Journal Club, looking into many different aspects of biomechanics. We're really excited to host Mathias Peirlinck today. He's been joining us as an audience member for pretty much the entire journal club that we've organized, and so I'm really excited to have him present his work today. Mathias got his PhD from the university in Ghent, right? Sorry that I didn't remember that right away. From Ghent, and then went on to Stanford for a postdoc. He also did an internship at Abacus, I think, for a little bit of time, which really makes him a true expert in anything related to Abacus, and I think it's a big part of his work. Following the gig at Stanford, he's now a tenure-track assistant professor at the Technical University in Delft, and I'm really excited to hear about your work today. Why don't you take it away?
All right. So hello, everyone. First of all, I would like to thank all you initiators of this initiative. For inviting me. Of course, it's an honor. Yeah, I've been seeing the talks before, so I know who has been before me, so a little bit stressed. But I'm looking forward to share my work here. And I was asked to give a talk about or give a closer look into our paper called Using Machine Learning to Characterize Heart Failure Across the Scales. So I'll get right to it. So what we're talking about is actually this paper. It's actually a paper from 2019 already. Time goes fast. Where I worked on cardiac growth and remodeling with Alan Kuhl from Stanford University and Francisco Sari Costabal from Pontificia Universidad Católica de Chile. I always try to say it correct. Please correct me if I'm wrong, Francisco. And also on this work was Kevin Seck from the University of Cape Town and Julius Guccione from UCSF. And then the next two people, maybe I should put my laser pointer on. And then the next two people here that you see are Susie and Ghassan from California Medical Innovations Institute, and Patrick Segers and Mathieu de Beule, my advisors of my PhD back in Ghent University. So let's look at the title, and I decided to go through the title step by step to sort of have this overall view into what we were working on in this paper. So we use machine learning to characterize heart failure across the scales. So we characterize the heart across the scales. So what we try to do, or what I try to do mostly in my work, is to understand the heart as a multi-scale multi-physics problem. And with multi-scale, I talk about the subcellular scale, where specific processes take place, both electrophysiological, mechanical, and so on. At the cell scale, there's different other processes, tissue scale as well. There's a lot of anisotropy there, both electrophysiologically and mechanically, for example. And then at the organ scale, we'll bring this typically all together in patient-specific geometries and with the typical myoarchitecture, for example. And then also at the population level, there's quite some variability, so things to learn on how the heart functions in between different patients. And then when I talk about multi-physics, what I talk about here is that the heart is pretty complex. Of course, there's a lot of processes happening. So we look at the electrophysiology, tissue mechanics, fluid mechanics, growth and remodeling, and also actually some imaging physics, but that's not really in this talk today here. So what does this lead to if we solve all these processes across the scales? So we have the living human heart model shown here, where we can solve the electrophysiology and how the electrical signal actually travels through the heart, which leads the tissue to contract. So we have these stretch states here that vary across the cardiac cycle, and we can then also use that to sort of compute the maximum principal stresses in the heart. And then if we take this one physics problem further, we can also couple this to the blood flow, of course, by solving fluid structure interaction problems, which are interesting to look at, for example, the wall shear stress on the wall, or specific effects of using different valves, or seeing how that leads to stretch and stress states in the valves, for example. So doing this, we have quite some opportunities in human heart modeling, both for cardiac pathophysiology, medical device innovation, personalized treatment strategies and regulatory verification. And I'm just misusing this opportunity to actually advertise a little bit for our review paper as well, where we discuss this all, of course. So I invite you all who are interested in this to also read up on this there. But of course, this talk today just focuses on the first part and a sub project of that part, which is an improved understanding in cardiac pathophysiology. So what cardiac pathophysiology do we want to look at here, which is in this paper, that's heart failure. So why heart failure? Well, if we look at the global burden of heart disease, there's actually over 26 million people worldwide that are diagnosed with heart failure, and that's actually just an underestimation. It's actually even more. There's some estimates of over 37 million people actually being suffering from heart failure. And then once you are diagnosed, you actually have 50% after you leave the hospital the first time to end up in the hospital again within 6 months after discharge. This also leads to the fact that this is the #1 cause of hospitalization, which also explains why this is pretty expensive to society. And then overall, if we look at the lifetime risk of developing heart failure, that's in every person, that's around 1 in 5, which is pretty big number. So for patients who have heart failure, the quality of life and survival rate is pretty poor, with over 45% of people dying within the first 5 years. And then combined with that, you have the aging population, the increasing prevalence of risk factors such as sedentary lifestyle or diabetes, for example, and improved post-myocardial infarction survivals nowadays that are actually leading to a rising incidence of heart failure in general. So this sort of is an intro into why heart failure is becoming a major and growing public health problem and why we need to pay close attention to this. If we then look at heart failure and the different phenotypes that there are, there's HFpEF, heart failure with preserved ejection fraction, where not a lot of therapies are proven to reduce morbidity and mortality. For heart failure with reduced ejection fraction, there are newer therapies which have improved survival rates, but there's still significant mortality. And for acute heart failure, there's not a lot of evidence that supports long-term benefits of the current treatment therapies. So what we are all after, of course, is to have an increased understanding on cardiac disease mechanisms. What initiates these pathophysiological processes in heart tissue, and what is driving it to progress further. And once we have that, then we can start looking at mechanism-targeted treatment strategies so that we can sort of counteract those mechanisms in a smart way so that we can hopefully one day provide better treatments for heart failure. So that brings me to the next part of the title, characterizing heart failure across the scales. And to do that, we look at multi-scale cardiac growth models, where we, again, as I said in the beginning, try to understand the heart as a multi-scale system, where events at the organ scale have an effect on the tissue scale, cell scale, and subcellular scale, and also the other way around. So that's sort of what I try to illustrate here. So for example, if you have a volume overload in the heart that causes the tissue to stretch, which causes cells to start some processes, which then lead to growth patterns in the subcellular scale. And then that again leads to changes going all the way up to the scales, which are then having their effect on how the organ behaves. And that, of course, evolves over time. So each of these processes sort of have their effect there. And then the typical way of modeling this, or one of the classical ways to model this, is the kinematic-based growth framework. So for everyone who knows some biomechanics, this might seem familiar or might sound familiar. But so in general, what we do is that we take a look at our initial potato and then have the deformation gradient that brings that to the updated potato. And that is sort of coupled together by the deformation gradient F, which we sort of decompose in the elastic deformation gradient Fe and the growth deformation gradient Fg. And so how this works is that the deformation gradient Fg sort of allows different parts of the potato to grow without being bounded to each other. So that becomes like this intermediate configuration here. And then you have the elastic deformation gradient Fe, which couples this all together so that it's actually a physical potato again. But then the question is, what defines this deformation growth, this growth deformation tensor? information tensor here, gradient here. And there's quite some discussion on that. We know that this is that mechanical stimuli play a role in this, but there's quite some ambiguity on how that works. So this is actually a nice overview by Wittenberg and Holmes from 2017, where you can see all these different kinds of growth laws that have been proposed in the past for cardiac growth and remodeling, some stress-based, some stretch-based in different directions at different points in time in the cardiac cycle. So there is still some discussion in the field on what is actually driving this. So just as an intro a little bit on what the most commonly used stimuli are that people are looking at for volume overload, for example, most people assume that volume overload leads to increased fiber stretch at the subcellular level, which then leads to longitudinal growth. So then the hypothesis there is the stretch-driven longitudinal growth, which you can sort of see displayed here. So the growth parameter theta here is driven by a mismatch or like a stretch state lambda E, which is higher than a certain critical stretch state of the cell that it wants to be in. And as long as that is larger than the lambda critical, it actually will start growing in the longitudinal direction. And then in the cross-sectional direction, the assumption there is that there is no growth. So if we put that into a multiscale heart model, what we see is serial sarcomere deposition due to this volume overload, which causes eccentric hypertrophy. And that actually leads to the decreased ejection fraction, which is sort of the hallmark for systolic heart failure. And then for pressure overload, there's a different hypothesis there that actually the stress felt by the cell at end systole or during peak systole at least will lead to transverse growth, for example, as shown here. So that leads to, once you are overcoming a certain critical stress state, that will actually lead to cross-sectional growth of the cell. And if we put that in a full-scale cardiac, multi-scale cardiac growth model, it leads to parallel sarcomere deposition, concentric hypertrophy, and then a stiffer ventricle, which makes which is sort of the hallmark of diastolic heart failure. So if we look at these multi-scale cardiac growth models, all the effects that we see here, subcellular and cellular level, make sense. Also, if we look then at the secondary effects at the organ scale, such as papillary muscle dislocation, error dilatation, regurgitant flow, and outflow obstruction. So qualitatively, that matches what we see in the clinically. But how does that match quantitatively? And that's a little bit the challenge that we were looking at in this paper. So first of all, cardiac growth and remodeling is highly patient-specific in its time course and extent of disease progression. So there's some need for subject-specific data collection and modeling in parallel. Its multi-scale nature requires us to measure and model different spatial and temporal scales at the same time. And then, of course, with experimental data, there's some intrinsic uncertainty that's associated with sparse experimental data itself, and that has a strong influence on the predicted outcome. So these three challenges make it difficult for us to quantitatively validate any of these hypotheses. So the way that we do that in this paper is by making smart use of a couple of machine learning techniques. And I will give a short intro in some of these that we used. I think one of the most important ones that we use here is Bayesian Inference, which is inspired by Thomas Bayes, an English statistician and philosopher from the 1700s, who proposed his theorem that describes the probability of a hypothesis or a set of parameters based on a prior knowledge and the observed evidence of that hypothesis. So what this theorem actually looks like in equations is the following equations, which has four different parts, as shown here by the colors. So this term here is actually the likelihood. So that expresses the probability of the evidence X, so your data, for example, given the hypothesis or the parameter set data, as you can see here. And then this term here is the prior. So this allows us to put our initial beliefs about this hypothesis or these parameter sets into our inference. And then you also have the evidence, Px, which is the probability of the evidence or X arising globally, which is a little bit more of a difficult term to compute, but I'll talk about that later. And then the final term, so what this actually leads to is the posterior distribution. And that's the probability of the hypothesis or the parameter set theta given the evidence X. And that's actually the one that we're after. We want to know for a certain hypothesis or parameter set theta, for example, here, how fast this grows, if the evidence sort of explains this, yes or no. And otherwise, we need to update our beliefs about theta, which we sort of do by setting up this posterior distribution. So as I already mentioned before, actually this evidence, so this denominator here, is difficult or almost impossible to compute, because this means that for any possible hypothesis or parameter set you can think of, you sort of need to add them all together to come to the full evidence of the data that you have seen here. So that's not really computationally tractable. However, we have Markov chain Monte Carlo, some sort of magic trick in our hands, which we can use to actually compute this posterior distribution without suffering from this limitation. So in a nutshell, Markov chain Monte Carlo methods are actually some class of algorithms for sampling from a probability distribution. In these words, you might recognize Monte Carlo in there, and that's of course independent sampling, as you know. And while these classical Monte Carlo samplers are just sampling independently without a next sample depending on the previous sample, that's just the difference with Markov chain Monte Carlo. So in Markov chain Monte Carlo sampler, we take into account information from the previous sample we looked at. So it sort of aims to build up a so-called Markov chain that, if we sample enough in the limit, samples from the desired target posterior distribution. So it's sampling a lot, looking at this computation here, and then if we do this enough, in the end, in the limit, we should end up with our posterior distribution. There's actually many different algorithms that are out there on how to set up these Markov chains, but just to illustrate how this sort of helps us doing Bayesian inference, I can give you a quick simplistic example of this. For example, take the example that we have the first sample being theta 1, a hypothesized parameter set, and the data X. Now then we can try to compute this posterior, this probability of this sample by computing this. But as I said before, this evidence is difficult to compute, so that's not easy to do. However, if we take a second sample, theta 2 here, and we compute this, try to compute this again, we have the same problem. However, we can use them together by dividing them by each other, and then this evidence sort of cancels out. And based on that, we can actually have a probability comparison between theta 1 and theta 2. So actually, if we can compute both these terms. So if we end up higher than 1 here, we actually are pretty sure that, oh, I switched this up, that theta 1 is more likely than theta 2. So we should accept new theta 1 actually here. Sorry for the typo. And then if it's between 0 and 1, some people would say just reject, well, because that means that theta 2 is more likely. However, to be smart about this, to still in the limit end up with a Markov chain that samples from the posterior distribution, you can sort of say aloud, well, let's make this the probability, this outcome, the probability of accepting a new theta 2 sample. So as an example of how this works, there's this little animation here that I wanted to share with you, and this sort of shows this sampling. So the blue region is actually the posterior distribution, which we don't see at the start. But by doing this sampling, so you see red and green, which means accept or reject the sample. And by doing this a lot of times, we actually will end up, so this is sped up, how we can end up with this posterior distribution by doing, for example, that approach, which is in this case shown a random walk Metropolis Hastings approach. There's different approaches out there, but this just was one of them that I want to share because it's easier to understand than one of the more complex ones. And then a second aspect, which will be important for the rest of the story, is Gaussian process regression. For those of you who don't know it, I'll try to give a coarse explanation of what it is. But in general, with Gaussian process regression, what we have is some data set D, which is a combination of input-output pairs, for example, as shown here for n samples. And we want to find a predictive function that actually explains y in function of x with some sort of noise or data uncertainty on top of it. And then a very coarse explanation of this would be, I think my slides are, okay, is that a Gaussian process can be seen as a probability distribution over possible functions that fits a set of points in this scenario. So I used Francisco's explanation for this because he can always explain this very nicely. So you have, for example, these prior samples of distributions, as you can see here, and then you can condition this on the observations that you have, and then compute the Gaussian posterior. You do that by learning a kernel function with hyperparameters theta, and that you can do again with the Bayesian inference that I explained to you before. So in the end, you have this function based on input-output data. And we will use this later to sort of overcome our problem of having to do computational models for each input pair if you have a lot of uncertainty, but you will see that later. Okay, so now finally I can go into the study. Sorry for the long intro, but I thought that was useful to have a close look into what we were doing. So this was our problem. This is what we wanted to look at, quantitative validation of the growth hypothesis. So what we did is that we had 6 peaks in which we induced systolic heart failure by creating mitral valve regurgitation, and then we studied the organ and the cell scale changes, both in experiments and in computer models. So first focusing on the experiments, what we did here is, so we first took organ scale measurements by echo at baseline and also histological samples to characterize cell scale changes at baseline. Then we cut through the mitral chordae to create volume overload. And then we waited 2 weeks and then again did organ and cell scale measurements. We did that at week 4, 6, and week 8. So that gives us the following data, as you can see here on the right. So we have from the echo, we have anti-systolic volume data, which changes over time for each of the peaks. And then on the cell scale level, we have myocyte length data, as you can see here for each of the peaks, and myocyte width data. So as you can see, this data is typical experimental data, which has its uncertainty in there, and it's not just easy to build a model that sort of has this volume overload at week 2, then this at week 4, 6, and 8. And there's also some uncertainty on this. So using this as absolute values is not ideal. So the way that we sort of overcame this is by making this hypothesis that the volume overload is log normally distributed with a certain offset for each and every peak, which you can see here with this A value, and then B times T, so that's the time dependence of this log normal distribution. And so then you can sort of learn for each and every peak the normal distribution of these 2 parameters, plus then the overall uncertainty for that specific peak. However, we have limited data here. So we used another trick here, which is hierarchical modeling, to actually do this a little bit better or more optimal. And that's what you can see here. So for each of these parameters for the peak, we assume that this comes from a hyperdistribution that sort of explains the whole cohort. Because each and every peak here underwent the same surgery, so the same mitral regurgitation that was created. And then that helps us explain what the general trend for the whole population is. And then the values that are here for each and every peak sort of explain how that peak is different from the whole population, or a part of that major population. And that actually helps us a lot, which I will go into that a little bit later. But so doing this with Bayesian inference gives us these results, which sort of shows the certainty and uncertainty that we have from this data. And as you can see here, which is what is very powerful about doing this hierarchical modeling, is that for peak 5, for example, we did not have any anti-systolic volume data at week 8, but then by incorporating the hyperdistribution effects from the whole cohort, we could still have some certainty on what the anti-systolic volume would have been at week 8 here. Same is true for there's another peak number 1 where we had this too. You can see that the color scale here is less dark, so we are less certain here than we are for other peaks, for example. But still, we can learn something from what happened at week 8 from the other peaks to sort of explain what will happen for that peak at an unseen data point. And for myocyte length and width, we did something similar. So this looks a little bit more complex, but in the end, it's the same kind of system, where we want to know how the myocyte length and width changes over time from a hyperdistribution. just the important difference here is that the noise is of course connected because every myocyte length measurement was coupled to a myocyte width measurement. So that should be coupled there. Doing this, we end up with this result here, where you can see that myocyte length really changed for most of the pigs, while the myocyte width sort of stayed the same for each and every pig there. Then we can move on to the computer models, which we did with the kinematic-based growth framework, as you can see here. So to describe the elastic deformation, we assign the Gasser-Ockern-Holzapfel material model for cardiac tissue, and then we did first a fit based on experimental data by Sommer et al., so the triaxial shear test data. But then, given that we had pressures and volumes, we actually optimized this to represent the in vivo stiffness of each of these pigs, because there is some difference always seen between data that you get from samples that are taken out of the body and, of course, how it behaves inside the body. And then for the growth hypothesis, we used the stretch-driven growth law for volume overload that I talked to you about before. This is a very simplistic one, but it was the first time that we wanted to test in this study. So for each and every pig, we simulated the volume overload and how that will lead to growth in the tissue. And given that the samples were taken from the mid wall and the apex, we compared our simulation results at these zones with these regions. However, we did not just have one volume overload for each pig. We had some uncertainty on that. So what we had to do is actually propagate the uncertainty of our volume overload through the models to get to an uncertainty on our outcome. And that's where the Gaussian processes actually come in. So we had 500 posterior samples for pig 4, for example, for the volume overload. And instead of doing 500 simulations, which we could have done, just would have been computationally expensive, we just took some samples. So we used 20 length hypercube samples to do 20 simulations and see how that leads to growth in each of these subject-specific ventricle models at least. So we did this for every pig. That's pretty important. And with that, we can learn the relationship between time and diastolic volume overload and how that leads in our models to longitudinal growth. And to make sure that this was correct, we did another test sample on another 10 simulations, and as long as our root mean square error is low enough, we are pretty okay with that. So we did this for each and every pig, and then propagated the uncertainty on our volume overload through our models to go to the uncertainty of our cell scale results. So then if we compare this was the result. So we can look at the evolution over time for each and every pig between experiment and simulation. And then if we look at the end of this, we actually get these histograms, as you can see here, which sort of shows how well the overlap is. For most pigs, or at least for pig 4, 5, and 6, this was very good. 1 and 3 were fine, but then pig 2 was clearly an outlier, and we're not 100% sure yet what happened there, if there's some inflammation happening or some other aspect that actually does not allow us to explain this completely in a good way. However, the conclusion of this is then that stretch-driven growth law explains 52.7% of myocyte morphology changes. And that's actually the result we were after. We now have a quantitative validation of a growth hypothesis. So that sort of was the study. The result of that, I mean, in general, in conclusion, we developed a novel approach to quantify the predictive power of cardiac growth modeling using tools for machine learning. We used a unique chronic volume overload study where we monitored growth longitudinally, biweekly, and across multiple scales. We used subject-specific computational ventricle models, calibrated the elastic response, and quantified the predictive power of the stretch-driven growth law. We quantified the uncertainty in experimental measurements using hierarchical modeling and Bayesian inference, and then propagated this uncertainty through our subject-specific computational ventricle models using Gaussian process regression. So with that, I conclude my closer look. However, I want to make use of the opportunity to also make some advertisement for more recent work that we also did, which I sort of mentioned here. So with that, if there's any questions, I'm more than happy to respond.
Thank you, Mathias. This was a really nice talk, very clear, a lot of explanations at the beginning about your methods, which I really appreciate. Who would like to go first? I'm going to check for raised hands, or just go ahead and unmute yourself. Gabriella, did you unmute? Oh, okay, there's an audio. So Tirius, do you want to go first?
Oh, wait, are you talking about the chat? I don't see it.
No, I'm looking. I think I'm just trying to see who unmuted in order to ask questions. But Emma has a question.
Yeah, thanks, Johannes. First of all, fantastic talk, really nice slides, and I really like how you kind of like led us up to what you actually did. That was really helpful. My question is a little bit abstract. So in this example, you had an experimental data set with 6 pigs. If you could have sort of like almost like the experimental data set of your dreams, or like something to add on to that, what would be most helpful? Like what could have helped inform your models better?
I think for this study specifically, longer would have been nice. You could sort of see that each of these pigs was still growing, or like the myocytes, for example, were still growing and remodeling. So made it a little bit more difficult for us to start looking into the time effects of growth, which we couldn't really do in this study. So that would be here, of course, very interesting as well. And then, yeah, more abstract towards the future. Like, I think the more histological information we can get, the more complex we can also make our growth models, because this is still kinematic-based growth framework, which has its, of course, its own assumptions in there, which, of course, are something to think about.
Thank you.
David, do you want to go next?
Yeah, sure. So thanks for that. That was really, really interesting. Nice presentation. I wanted to ask you a question about, I guess, kind of how we can, another way of thinking about how we validate these growth models. So, I mean, one thing we know is that inducing growth is going to yield some change to the geometry, but also yield some pattern of residual stress. And so in theory, if you took those hearts that you had and then you excised them and you did those classic opening angle experiments, you would be able to see what sort of residual stress release you might get. And then that would be something to compare with what you have from your kinematic growth that you deduce through the modeling. And from what we've tried, so we've done this, we don't have the data, but we've just done it with numerical experiments. If we basically induce growth and then we take a slab out of our heart and then we do this pseudo opening angle, it never looks like what you see in data. It always, when you apply these sort of either a long fiber or a cross fiber growth patterns, and it seems like they never match. They do weird things like twisting that has never been reported. I don't know, have you looked at this at all? Or have you thought about that aspect of growth?
I have thought about it, but I think the intrinsic challenge there is also, where do you start? Do you start with a model that already has residual stresses in there? I know there's also some papers that have looked at just doing that with kinematic-based growth modeling. So I think you would definitely have to do both aspects of this to see how you first have your residual stresses, and then if you cut those open even before growth, do they match? And once we have that, then we can start, I think, looking at growth and how those remodeled or grown parts then respond differently, hopefully. I think that would be actually pretty interesting to do. For this study, they were not cut open in that way, so we don't have the data on how they open, unfortunately. But that's something that also alludes to Emma's question, I think. Like, ideally, we would have had that data. So yeah.
Okay, Dr. Giesen, do you want to go next?
Hi, Mathias, great talk, thank you. I was just wondering a bit about the hyperdistribution that you were talking about. I think that's a very crucial aspect in your uncertainty quantification, and also one that is really potentially very important in finding missing data points in experimental or sparse experimental data sets. Could you tell me a bit more about that, how you get those distributions and where they're springing from?
Yeah, so let me just go back to this one slide to sort of have something to refer to. So the idea here is that for each and every pig, for example, what we had here was, this was our assumption, of course, that that these hearts grow log normal. And whether or not that is true is also already a question which is a little bit difficult to think about. But given that our uncertainty does not become like, is not a weird shape that is only like bounded in the middle, for example, already sort of makes this okay to assume. But then the idea of the hyperdistribution is that each and every pig and how it behaves with that assumption is coupled to how the whole cohort is changing over time. Given that they have the same conditions, that's interesting. So for example, if you have an experimental data set of a population that is classified the same way from a clinical phenotype kind of way, for example, this isn't a thing that you can do. You can even bring that one level up and even create a hyper distribution then to sort of say what the whole population is doing, then how specific cohorts are behaving, and then how the individual is behaving. We actually did this in, Amelie Schaefer did this in the paper on Bayesian inference on Alzheimer's disease, for example, to look at specific proteins in the brain and how they are traveling through the brain, for example. And there was this assumption that amyloid beta and amyloid positive and negative are the two cohorts to look at, for example. So then you can have these two hyperdistributions. So how that is different for different population groups, for example.
And how do we know that a certain population behaves according to this distribution? Because well, I think for big data, we don't have that much data around.
Yeah. So you sort of can look at how that hyperdistribution then looks. So if there's huge uncertainty, or if you have two cohorts, for example, and there's no clear shift between the two distributions, that sort of shows that this was not the best assumption to make, because then this clearly does not explain that there are two populations there. So then the question is sort of like, do these two cohorts make sense? So it's by looking at these hyperdistributions and what their result is that you can sort of look at whether or not this assumption was a good one to make. I'm not sure if that is making it more confusing or just not.
Yeah. I think we'll need some more time to discuss this, Mathias.
Sure, we have the chance to.
Yeah.
Ashanur, do you want to go next?
Yeah. Hello. Thank you for the presentation. I'm not sure whether you mentioned this or not, but I wanted to ask, why did you end up using Bayesian inference and the Gaussian process regression as your final machine learning algorithms to use for this problem?
That's based on our experience, and we were confident to work with, to be honest. We had some successes. Mostly Francisco had some successes with this before we started this study, and that's why we used this. I'm still using Bayesian inference quite a lot. We have used it for quite some other subjects, as well as some COVID outbreak dynamics, for example, recently. And it's a pretty flexible tool that actually has helped us a lot already to analyze data like this. So that's sort of why we looked at this. It allows us, as I said in the explanation, it allows us to put prior beliefs in this. So like if you don't know anything, you just choose very informal prior so that you don't make too big of an assumption of what the data is like. But if you have information, it also allows you to put that in there. If I know that for each of these pigs, they will grow, for example, then I can put that as a prior belief in this formula. I don't know how many slides ago that was. Here, for example, in this data, then I can put that information there, which again gives us quite some flexibility to work with. So that's a nice thing about using Bayesian inference for these kinds of things.
Okay, thank you.
I don't see more raised hands, but is there someone who would like to ask something? I think in the limitations part of this paper, you actually mentioned that had you known that you would use this method, you would have considered sampling from the animals differently. Do you have any higher level thoughts on how to design experiments in the future, given that we technically could conceive of models where we have fairly high confidence, or we could sort of quantify our uncertainty, how to sample from few animals if the experiment is very example, how would you go back basically to design your experiment better?
Yeah, that's sort of something indeed we were thinking about after we did the study. Is like, for example, I brought this slide up to answer this question because say, for example, that we would have wanted to grow these pigs longer, but every time we do this histology quantification, that costs money, of course. So if you're on a limited budget, what you can think of is doing, well, if we first of all did the first 3 pigs and we see this evolution and we already have some idea of the uncertainty, we can, for example, here, in that case, say, well, at week 8, our uncertainty is not that good. We should, like the next pig, maybe we should just look at it at week 0 and week 8 then, for example, and then do longer. So it allows you to sort of sample at the time where your uncertainty is still large so that you can sort of bring down the uncertainty from your hyperdistribution in that way, so that you can sample smartly and maybe save some stress also for the animals to go through, so that you can only do the histology, the biopsy sampling, for example, at specific time points based on what you saw in the previous pigs already. So that would involve just doing Bayesian inference on the pigs you already did before, in this case. And then if you have another pig coming in, while being smart about your time points where you sample. You can do that also with some other machine learning techniques, such as active learning for where you want to bring down the uncertainty that you have on your uncertainty that you quantify.
So another question from my side, Mathias, just illustrating my ignorance on this topic. Would there be a benefit of sampling pigs at different time points? Because intuitively we do that at the same time point, but is that a good approach, or is there a benefit to doing it at different time points for different animals?
So the way that why we mentioned this in our paper was just out of sort of this, if you have a limited means of where you can sample, or you want to limit, for example, the amount of in vivo manipulations that you do on an animal, you could sample at the time points that you want. So that would be the reason mostly to do this, like to make sure that you don't sample in a time zone, for example, here where you already had quite some certainty, because the added point there might not really help you much more to bring down this uncertainty. So for example, if you say, well, for pig 3 here, I think this uncertainty is fine. That's sort of within the realms of what I think is what we can achieve for this measurement. But here, this is too large. Well, okay, then pig 4, definitely focus on maybe sampling at week 7, 8, and 9. That's sort of what I'm aiming at. But then, of course, your pig needs to be, or like your animal studies need to be all representative enough to belong to the same cohort, which is also a challenging assumption maybe for some.
Well, I guess it's all about how to optimize these pig experiments or animal experiments, I guess, design-wise, to reduce the number of animals that we need. So from that perspective, I guess it is really very valuable.
Yeah, indeed. Like if you have this assumption that you need 10 pigs because that for example, that 10 pigs are what I need to bring down the uncertainty. Well, maybe you can first do 5 and see what the uncertainty already is that you have, and based on that, making a follow-up decision.
Christine, do you want to ask a question?
Yes. So thank you, Mathias. It was a really great talk, and I really enjoyed all your great animation that you showed us. So first of all, I have some sort of modeling question. So basically, I was wondering, was your model able to reach to a steady state when it was predicting the LV growth under volume overloading? And if or was it kind of like kept growing and it was not able to reach the steady state? And my second question was that was your model only able to predict the ventricle dilation, or was it able also to predict the reversal of that? I'm curious what would happen if the volume overloading was kind of reversed in your model. What would be happen in your model? And if not, what's your thought on this, and why is that for example, capturing the reversal of growth is kind of challenging for all the people in modeling field? Thank you.
Yeah. So to answer the first question, these hard growths, if there's no volume overload going on further, then this will stop. Like they will reach a steady state with this growth law. I did quite some simulations there to check whether or not this holds. So for this growth law, that does happen. If the stimulus sort of does not keep increasing, then it's fine and it will reach a new steady state. To answer the second question, that is possible to do. We haven't done it though, because we also did not really have the pressure volume loops to start looking at the different contractility, for example. That's something you can look at then later, because if you have indeed a grown heart, which is like dilated, that will have its effect there as well. So we haven't looked at it, but it's something we could do if we couple the active function to that and make an assumption on whether or not that changed or not. And then just look at the geometrical changes, for example, on how that would already have its effect, and whether or not there's something else that we need to put in our growth models to explain that better.
Thank you.
I'll take this conversation in a different direction with the following question. Abacus, or the Living Heart Project, has a large interest in using computational modeling for in the FDA approval process of new drugs, for example. So can you just generally talk about what are the, because I would assume that you're aware of what's going on there. Can you say for the modeling folks out here, what is the FDA interested in, or what are their key concerns about these multi-scale or organ level simulations? What are they after in order to feel confident that they should be including this in their approval pipelines?
Yeah, I think the main concern and thoughts about the FDA on this is standardization. How do you standardize computational methods? How do you make sure that every code is properly verified, validated, and tested? How do you make sure that these predictions for example, for the stretch-driven growth here, as an example, just like how do you make sure that these are true? So I think from that point of view, they have been launching some documents on how they visualize this needs to happen. I think for them, the interest there is like, how do we set up appropriate protocols to do computational modeling in such a standardized way so that you can objectively confirm models across different softwares, across different research groups, open source, commercial, versus each other, which is a challenging thing to do. But on the other hand, there are benchmarks out there which are always interesting to do this with, right? And that's the problem. Like, how do you verify something just one by one? Well, the nice thing to do is if you do it with 8 or 10 groups, you can see how that compares to each other. It's been done for cardiac mechanics. It has been done for cardiac electrophysiology. These are some pretty well-known benchmark studies. So I think there lies a good way for doing this. And of course, yeah, the FDA together with the Living Heart project, is also like setting up this study where they're looking at mitral valves and how to optimize them, for example. And I think they're following along to see how this process goes with multiple partners involved, where I guess for following the experience itself is interesting for them to see how they can steer further towards this in the future. Because nowadays you see that regulatory agencies more and more start asking these results as an add-on to animal studies, or even partially like a replacement of part of it, at least. I wouldn't say more than that, but that's why it's also important to standardize it, because you want to make sure that what comes out of that is correct if you are going to use it as part of your validation for a new device, a new drug, for example.
Okay. If there's no additional question, then I think with the remaining time, do you want to pitch anything else? Do you have open positions? Are you looking for PhDs, postdocs?
I'm looking for a postdoc. So if anyone's interested, always let me know. And I'm always interested if anyone wants to work on this with me. Just shoot me an email and we can always talk and see what we can do. Yeah, and I mean, I think I already misused my time enough to refer to these other papers. There's one that we recently published, Francisco, Ellen, and I, on sex differences in drug-induced rhythmogenesis, which was a pretty fun study to look at. I have a talk on this for the cardiac physiome that's also on YouTube. So if anyone wants to see the talk, I'll refer them to that, or always just shoot me an email. I'm happy to jump on a Zoom call, which is so easy nowadays anyway. So happy to talk about those things too.
All right. Well, thank you so much, Mathias. This was a great addition. So
yeah, thank you for the invitation.
On your